In the heat treatment of metals and alloys, the quenching operation may appear to be a fairly simple process. Metal parts are heated to a high temperature, then cooled rapidly, usually by plunging the part into a tank of oil or water or some other liquid solution. But parts can also be quenched in a gas, and sometimes by contact with a cold solid material. The fact is, there are many ways to quench a heated part, and the methods of quenching vary from alloy to alloy. The quenching media will vary depending on how fast the alloy is to be cooled, or how slowly, or to what temperature it must be held before cooling completely to room temperature. Sometimes different quenchants must be used for the same alloy, only because the section thickness of the workpiece may be different. Picking the right medium and mode of quenching for the specific parts being heat treated depends entirely on the type of metals and alloys we are treating, the size and geometry of the parts we are treating, and the purpose to which these parts will eventually be used. But despite the many variations in the quenching process, one thing is common to all quenching. All methods and modes of quenching involve the rapid cooling of an alloy from a high temperature. This is what quenching is all about, the rapid cooling of an alloy from a high temperature. Quenching, the metallurgical principles. A metal or alloy is quenched during heat treating for any one of three basic reasons. 1. To harden the material. 2. To soften the material without degrading its resistance to corrosion. Or 3. To prepare the alloy for hardening by precipitation. In all three cases, the operation is the same. The alloy is rapidly cooled from a high temperature. But in each case, the purpose and the result will be different. Only one of these reasons will apply to any given material. Hardening is the main purpose of quenching in the case of a large group of steels, which include plain carbon steels, low and high alloy steels, and tool steels. When these steels are heated to high temperatures and quenched, a hard and brittle phase is formed. This is called martensite. A special class of steels called austenitic stainless steels responds quite differently to quenching. These steels remain soft when quenched. The purpose of quenching is to maintain their resistance to corrosion. More about this in a moment. Non-ferrous alloys are quenched for still another reason. They are quenched from a solutioning temperature in order to retain the alloying elements in solid solution. This is a process that prepares the alloy for subsequent hardening by a controlled thermal treatment called precipitation. In some aluminum alloys, the hardness of the quenched workpiece is increased by leaving it at room temperature for a long period of time. This is called age hardening, or simply aging. Metallurgists now understand that this, too, is precipitation hardening. In each of these three cases, quenching is simply the rapid cooling of the material. However, depending on the alloy being quenched, the quenching can lead to very different results. To summarize, quenching carbon steels, tool steels, and alloy steels leads to hardening. Quenching austenitic stainless steel prevents the loss of corrosion resistance while retaining the ductility and toughness of the material, which is another way of saying it retains its softness. And quenching leaves non-ferrous alloys in a soft condition, ready for hardening by precipitation. Hardening by quenching. In the heat treating facilities where ferrous alloys are processed, the primary purpose of quenching is to harden. The materials treated are usually the carbon steels, the low and medium alloy steels, and tool steels. These materials are heated to high temperatures, then quenched. Typically, the quenching process is followed by tempering, which involves heating and then cooling again. Tempering is done to reduce the brittleness that rapid quenching produces in steels. When steel is heated to the austenitic temperature range, both ferrite and carbide phases disappear. All the carbon atoms now occupy positions within the crystal lattice of iron atoms. There is only one arrangement of all the atoms, and this is called austenite. If the austenite is cooled slowly, the carbon atoms will not remain in the iron lattice. Instead, they will segregate out as particles of iron carbide. If the austenite is quenched rapidly, the carbon atoms remain trapped within the crystal lattice because the segregation of carbon atoms in the form of iron carbide requires a time and temperature-dependent process called diffusion. Quenching, that is, rapid cooling, forces the carbon atoms to remain in solid solution in the iron, even when the temperature is well below the lowest temperature at which austenite is stable. This causes a distortion of the austenite. This distorted lattice is martensite. Softening by quenching. The difference between austenitic stainless steels and other ferrous alloys like plain carbon steels is that austenitic stainless steels do not go through a phase transformation when heated. Their crystal structure is always austenitic at high temperatures and at low temperatures. The alloying elements in austenitic stainless steels actually increase the range of temperature in which the austenitic structure can exist. However, an austenitic stainless steel can be hardened by working. For instance, when the austenitic stainless steel is stamped to make a sink or cold rolled during processing, it is work hardened and must be softened again by heating and quenching. And here's what's unique about quenching austenitic stainless steels. They must be quenched rapidly, otherwise they become susceptible to corrosion. Stainless steels are corrosion resistant because they contain chromium. At high temperature, the chromium atoms are evenly distributed in the crystal in a solid solution. And if an austenitic stainless steel is cooled quickly from a high temperature, the chromium atoms tend to stay in solid solution. But if an austenitic stainless steel is cooled slowly from a high temperature, the chromium atoms tend to combine with the carbon atoms. Chromium carbide will form near the grain boundaries. The material surrounding the grain boundaries is left deficient in chromium. Less chromium makes these areas of the steel less resistant to corrosion. This phenomenon is called sensitization. Quenching prevents the formation of chromium carbide and retains the chromium atoms in solid solution. Therefore, the corrosion resistance of the austenitic stainless steel remains undiminished. Precipitation hardening by quenching. The process of heat treating non-ferrous alloys is basically the same as for ferrous alloys, but the heating for treatment is called solutioning. It might help us understand what can be achieved by quenching a non-ferrous alloy from a solutioning temperature if we consider the aluminum-copper binary phase diagram. Let's consider an aluminum-copper alloy containing 4% copper by weight. In order to fabricate a useful shape from this material, we may forge the material, or extrude it, or roll it. And this mechanical working of the alloy requires a temperature at which all the copper is in solid solution. As the forging or the rolled plate cools slowly to room temperature, the ability of the aluminum lattice to hold the copper atoms in solid solution decreases. This means that more and more copper atoms leave the aluminum lattice and form particles of phases which are rich in copper. During slow cooling, these particles grow in size and become distinct from the aluminum lattice. As a result, the microstructure consists of an aluminum lattice containing a few copper atoms in solid solution and large particles of copper-rich phases. This structure is low in strength and low in toughness. In other words, it is useless as an engineering material. Therefore, a heat treater heats this work-hardened material to a temperature at which all the copper atoms are in solid solution, and then quenches. This helps retain the copper atoms in solid solution even though the alloy is no longer hot. Once quenched, a modest heating allows the excess copper atoms to form extremely small clusters that are uniformly distributed throughout the alloy. These clusters are so small that very high-resolution microscopes, such as electron microscopes, must be used to observe them. These clusters retain a definite structural relationship with the parent aluminum lattice. That is, they are coherent with the parent aluminum lattice. In this condition, the alloy possesses high strength and hardness, along with useful ductility and toughness. In other non-ferrous alloys, particles of phases rich in alloying elements need not be as small as those in aluminum alloys. However, the metallurgical phenomena are similar. So we see that in all classes of alloys, the carbon and alloy steels, the austenitic stainless steels, and the non-ferrous alloys, the quenching process is actually a means of retaining the atoms in the arrangement that exists at the high temperature. In effect, what quenching does is freeze the high temperature structure so that it can exist at room temperature. Quenching media and modes. Development of a large number of alloys for a variety of demanding applications made it necessary to develop several types of quenching media and quenching modes. Liquids are probably the most common quench media in heat treating, water being the most common. But there are 4 basic types of liquid quench media. Plain water can be used, and also a great variety of water-based solutions. Water can be mixed with polymers and caustic soda and other substances that will affect the severity and rate of cooling. Water is also the cheapest quenching medium. Another type of liquid quenchant is oil. The oils used for quenching are specially formulated for various alloy compositions. Molten salt is also considered a liquid quenchant. Salts melt at elevated temperatures, and they make effective quenchants to hold alloys at specific temperatures. Finally, molten metals can also be used as quenchants. These are typically pure metals or alloys with low melting points. In addition to liquid quenchants, gases can also be used to quench. There are 2 types of gas media: air, which is air right out of the atmosphere, and there are inert gases that can be used to quench, primarily argon and helium. Selection of quench media. The selection of a proper quench medium is extremely important when heat treating parts of specific metals and alloys. The quenching medium, as well as the mode of quenching, must be selected to provide the proper cooling rate. The proper cooling rate will depend on the alloy composition of the parts, the geometry of the parts, and the size of the load. Alloy composition and the phase consistency of the alloy determine its physical properties, such as thermal conductivity, its density, and specific heat. These physical properties determine how fast the alloy can cool in a given cooling environment. Selecting a quench medium that provides the proper cooling rate for the alloy composition and the part configuration is important to assure cooling the workpieces evenly without distortion or cracking. The isothermal diagrams and continuous cooling transformation diagrams help us predict the phases that will form during quenching. This is a continuous cooling diagram, or CCT diagram as it is usually called. These curves indicate the time and temperature at which the alloy begins its transformation from austenite and completes its transformation. For instance, a 1/16 diameter rod of this material will cool fast enough to miss the nose of the curve and transform completely to martensite. By comparison, a 1/4-inch diameter rod will take longer to cool and thus produce different phases in the material. The effectiveness of the quench, that is, the ability of a quenching medium to carry heat away from the parts being quenched, depends on several factors. Some of these factors can be controlled by the heat treater. For instance, a quenching liquid can be agitated. The speed of a water quench can be increased by dissolving salts in the water. Sodium chloride or caustic soda in water solution greatly increases the cooling ability and therefore the speed of the quench. To reduce the cooling ability of a water quench, certain polymers can be dissolved in the water. Using oil for the quench provides an even slower cooling rate. And for still slower cooling, the parts can be cooled in air. Liquid quenchants. When quenching in liquids, certain things occur that do not occur in other quenching media. One thing peculiar to liquid quenchants is the vapor blanket. This is the first of 3 stages of quenching, the A phase. When a hot piece of metal is plunged into a relatively cool liquid, the liquid in contact with the metal boils instantly and vaporizes. A vapor blanket or pocket of bubbles forms around the part. This is the vapor blanket, which tends to insulate the workpiece from the quenching liquid. This vapor blanket can affect the severity of the quench. During this A phase of quenching, the cooling rate is extremely slow. The B phase of the quench is the vapor transport phase. During this second stage of cooling, the vapor film has completely collapsed and there is rapid heat transfer along with violent boiling as fresh, cool liquid continually contacts the surface. The C phase of quenching is the liquid cooling stage. The surface temperature of the part has been reduced to near boiling. No more boiling of the quench fluid occurs. The rate of heat extraction is again reduced to a level much slower than that measured in the B stage. This phase of quenching is sometimes called the tail-out. Agitation of a liquid quenchant helps break the vapor blanket and promote a faster heat transfer. Quenching problems. Problems associated with quenching relate to both the material being quenched and the operators doing the quenching. For the metals and alloys and workpieces being quenched, the problems of cracking, distortion, and discoloration are always present. The knowledge of alloy metallurgy and behavior of various quenchants allows a heat treater to produce parts to customers' specifications without reworking and without causing excessive distortion. Summary: understanding quenching. Quenching is the rapid cooling of an alloy from a high temperature. Quenching methods vary depending on the alloy, how fast the alloy is to be cooled, how slowly it must be cooled, and the temperature at which it is held before cooling to room temperature. A metal or alloy is quenched for one of 3 basic reasons. Certain steels are hardened by quenching. Austenitic stainless steels are softened by quenching to maintain their resistance to corrosion. Non-ferrous alloys are solutioned, then quenched to prepare them for precipitation hardening. Heating an alloy to high temperature puts all the atoms in a solid solution, that is, a single crystalline structure. Quenching rapidly retains the atoms in the arrangement that exists at the high temperature. There are 4 basic types of liquid quench media: water and water-based solutions, oils, molten salts, and molten metals. Several types of gas can be used for quenching: air and inert gases. The proper cooling rate assures cooling evenly without distortion or cracking. Cooling rate of a quenchant depends on the alloy composition of the parts, the geometry of the parts, and the size of the load. Predicting the phases that form during quenching is done with isothermal diagrams and continuous cooling transformation diagrams. Effectiveness of the quench depends on agitation of the quench, the dissolved salts and polymers, and the type of quenchant, liquid or gas. Liquid quenchants cool in 3 stages. A stage, the vapor blanket. B stage, the vapor transport phase, and the C stage, the liquid cooling stage.